When you look around you, what do you see? You might see a cup of tea on your table, a book sitting on a shelf, or perhaps the clouds drifting lazily across the sky. Everything appears solid, continuous, and whole. The world seems to flow smoothly from one moment to the next, like a perfectly rendered film with no visible frames. We move through space without any bumps or jumps, and time seems to tick by in an unbroken stream. This perception of a seamless reality has been our trusted guide for all of human history, shaping our intuition about how the universe works. It feels so natural, so fundamentally right, that we rarely stop to question it. Sir Isaac Newton's laws of motion and gravity described a world where objects move through an absolute, unchanging space. His mathematics painted a picture of a perfect, predictable cosmos, where everything could be calculated with infinite precision. In this classical view, space and time were the featureless backdrop against which the drama of the universe unfolded. Then, at the dawn of the 20th century, Albert Einstein completely revolutionized our understanding of this cosmic stage. He showed us that space and time are not separate entities, but are woven together into a single, dynamic fabric he called spacetime. This fabric is not flat and rigid. It can be warped and curved by mass and energy. It is this curvature that we experience as gravity. The German physicist Max Planck discovered this at the turn of the 20th century, while studying heat radiation. He found that energy could only be emitted or absorbed in discrete little packets, which he called quanta. It was as if energy came in tiny, indivisible bricks. Stranger still, tiny particles like electrons seem to be both particles and waves at the same time, their true nature depending on how you chose to observe them. To give you a sense of just how infinitesimal this scale is, if you were to magnify a single atom to the size of the entire observable universe, the Planck length would be about the height of a single tree. Many physicists believe that the Planck length is not just a mathematical curiosity. They suspect it may represent the physical size of the fundamental pixels of space. Loop quantum gravity proposes that the fabric of space is not fundamental. Instead, it is woven from something more basic, tiny, indivisible loops. Imagine space as a colossal, intricate piece of chain mail, constructed from an immense number of interlinked rings. String theory proposes a beautifully simple idea to unify them all. It suggests that if you could zoom in on any of these particles, you would find they are not points at all. It's a bit like a violin string. The same string can produce a whole range of different musical notes depending on how it is plucked. However, for the mathematics of string theory to work, it requires something extraordinary. The universe cannot just have the three dimensions of space and one of time that we are familiar with. Fortunately, the universe provides us with exactly what we need: gamma-ray bursts. These are the most powerful explosions known in the cosmos, brighter than a billion suns. Telescopes like NASA's Fermi Gamma-Ray Space Telescope are designed to detect these bursts. They can measure the arrival time of individual photons with incredible precision. Imagine a credit card with a security hologram of a bird. The bird looks three-dimensional, but all the information needed to create that image is stored on the flat, two-dimensional surface of the card. The holographic principle proposes that our entire universe might work in a similar way. The three-dimensional world we experience could be an illusion projected from a two-dimensional hard drive at the edge of the cosmos. An experiment called the holometer was built at Fermilab in the United States, specifically to search for this holographic noise. After years of careful data collection, the holometer experiment announced its results. It found no evidence of the holographic jitter it was designed to detect. If spacetime is indeed made of fundamental, indivisible units, it would represent one of the most profound shifts in our understanding of reality since Einstein. This suggests that the universe itself might be fundamentally computational. The laws of physics could be seen as the algorithm that processes this information. We've journeyed from the clockwork cosmos of Newton to the flexible spacetime of Einstein. We've plunged into the bizarre, lumpy world of quantum mechanics. And now we stand at the edge of our knowledge, peering into the deepest question of all. What is the ultimate nature of reality? Is the universe a smooth, continuous canvas, as it appears to our senses? Or is it a breathtakingly detailed mosaic, assembled from an immense number of fundamental, indivisible pixels of space and time? This question represents the ultimate frontier of modern physics. The stakes could not be higher. We're using the full power of our intellect and technology to ask the most fundamental question imaginable. Whichever path the universe has taken, the quest to find out is a profoundly human endeavor. It's driven by the same curiosity that led our ancestors to look up at the stars. The search for the true nature of space-time leaves us with a universe filled with more questions than answers. Or perhaps the answer will come from a completely unexpected direction. A moment of insight from a young physicist, much like the one Einstein had in the patent office over a century ago. We're like cartographers of old, sailing into uncharted waters with only rudimentary maps and the stars to guide us. The mystery itself is a powerful engine for discovery. As we stand here today, on May 24th, 2024, we find ourselves in a truly remarkable moment in the history of science. It'll be written by the next generation of scientists, dreamers, and explorers. The mystery of space-time is the great challenge of our time, and its solution awaits us somewhere out there in the cosmos, or deep within the equations yet to be discovered.